Good morning, chemistry. We're going to set you up for a little more math. This week so far, all we've done is really kind of remind you about acids, bases, and how water self-ionizes, so you can use that for pH stuff. But what we're going to talk about today is really strong and weak acids and dissociation. We know from solutions that if we throw anything into a solution, that it will dissolve in some respects, especially ionic compounds. It will separate into its ions, which is why things like water and water-based solutions conduct electricity. Okay. This is especially important for acids and bases because really pH can tell you if it's an acid or a base. It really can't tell you if it's a strong acid or a base. And that makes a whole lot of difference in stuff. For example, I'll use this. You go to, well, right now, takeout. You go take out a delicious salad with maybe a vinaigrette dressing. Well, vinegar is acetic acid. It's a weak acid. You want it to be a weak acid. You don't want to be eating a strong acid. You don't want the citric acid in your fruits being a strong acid. You want them being a weak acid. Can you imagine if you put your vinaigrette dressing on your salad and the whole thing started to smoke and dissolve and you tried to put that in your throat? Bad mojo. Anyhow, so really what tells a strong or weak acid is how many hydrogen ions separate from the compound. And so that's what we're going to look at here. So an acid, we know, is if I throw it in solution, an acid is anything, and this is a general formula, anything starting with H. So I have the hydrogen attached to whatever the anion is. And I'm going to put it into, I'm going to dissolve it in water, and it's going to separate into hydrogen ions and what's called a conjugate base is, or the corresponding anion is whatever. And the more that, and it's an equilibrium, so the more that this happens over this, then the stronger it is. If you remember with water, this equilibrium where water separates into water and hydroxide, hydrogen and hydroxide, this equilibrium number was 1 times 10 to the minus 14th, very small. Almost all water is still water. Now, like everything, even in solution, it's not like these they just fall apart and are done. It's an equilibrium. So this acid compound is separating into ions, then they're coming back together. Separating into ions and coming back together. The question is, when it hits equilibrium, are we more on this side or are we more on this side? With water, with that number being 1 times 10 to the minus 14th, we knew we were basically on this side with very little ions, enough to conduct electricity and do the stuff water does, but whatever. We can do the same thing for acids. And again, it's always product over reactant when you're writing the equilibrium expression, as we've learned in our last unit. So it's always the ion concentrations, the ion molarities, here we go, the ion molarities divided by the compound molarity. And then whatever that number is, that equilibrium number is, will give you an indicator whether it's a strong or weak acid. Now, the same thing is true, but we're only going to walk through this talking about acids, but it would be the same exact thing for bases. Okay. Now, instead of calling it the equilibrium constant, they call it the acid dissociation constant, or Ka. If we were talking about a base, it would be Kb, and it would be the same thing. Okay. The higher that number, the stronger the base. The lower that number, the weaker the base. Okay. So the larger this number is, the stronger the acid is. All right, let's show you a chart. Here's your strong acids, and you'll notice how big those numbers are. They're up in the millions. This is, let's see, 10 to the 9th is a billion. So this is like 10 billion, okay? Which means that really something like hydroiodic acid is almost all hydrogen ion and iodine ion, and just the barest amount of compound to keep the equilibrium flowing. Same with hydrobromic acid. Same with, while hydrochloric acid, your stomach acid, is not quite as strong as these, it's still 10 to the 8th is still 100 million. Okay, so it means really for strong acids, the term is completely dissociated. While you never get rid of that teeny small amount of compound so that the equilibrium keeps going, there's so little of it that really it's all ions. Now you get in the Midland range here with trichloroacetic, oxalic, sulfurous. Notice that they're a little under 1. Those are, they're kind of intermediate. The dividing line between strong and weak and kind of some middle and ground in between there is really subjective. There's not a, scientists don't agree on where to plot the number down. They kind of argue, but we'll see that in a second. And then what you see here in the, whoops, one too far. In the blue here, what you see are weak acids. Carbonic acid, hydrocyanic, hydrofluoric acid. Really weak acids, look at those numbers. They don't like to be dissociated. They like to spend most of their time as compounds. Very little of it is hydrogen ion and conjugate base. And so they have numbers well below 1. That's the idea. This, far more than pH, tells you the strength, the equilibrium constant, basically, the dissociation constant. Far more tells you what a strong acid, strong base would be based on those numbers. All right, so let's look at strong acids like hydrochloric acid. It is going to be in an equilibrium where some of it is going to be compound, but it's going to be rolling back and forth between dissociating ions, coming back together, dissociating ions. But at any point in a solution, it hits equilibrium. And so you have a balance where the concentrations, again, going back to our last unit, the compound concentration, the ion concentration of both the hydrogen and the chloride all become constant. Even though they're constantly rotating back into being compound and not compound, because it's going at the same rate, those are constant. And so we can put it in the dissociation expression, and that's where the 10 to the 8th number comes in. You just plug in the molarities, multiply these two, divide, and there you go. In general, although again, there's no firm dividing line, anything over 1 is considered a strong acid. Because if you think of what 1 is when they're both equal, when you have as much compound as you have ions. So anything over 1 means you're favoring the dissociated ions where, and again, the hydrogen ion is what does all the acid work. The compound itself does nothing. Compounds are neutral. They don't do anything. There's no reaction. There's no acid stuff. There's nothing going on. Okay. All the activity of an acid is based on the hydrogen ion, that proton. So this is a strong acid because by the number 10 to the 8th, it's got a boatload of these in solution, the ions separated out, of which then you've got a whole lot of hydrogens to do acid work. And that's why I said anything over 1 is a strong acid. And really what they say then is completely dissociated. And so it's very easy. For strong acids and low pH numbers, yes, a low pH number can tell you it's a strong acid. Because essentially the pH and the concentration are, there. It's hard to get you can't get a weak acid down to low pH. It's like impossible. There's just not enough hydrogens in solution to get that pH number low, to get that concentration low. But for strong acids, absolutely. All right, let's look at a weak acid. Now, here it's the same thing. The hydrofluoric acid is going to be in some equilibrium, breaking into hydrogen ions and fluorine. But remember, the fluorine is the most electronegative element on the planet, on the whole periodic chart. So this very strong and this is true of all weak acids, they have a very strong conjugate base that wants to be bound, that wants to be compound. So that's why when I plug in all the molarities here, the number's less than 1, and you can see what they say with, again, not that great dividing line. A weak acid, the acid dissociation constant, that equilibrium constant, is generally below 0.01. Okay, and you can see that 3.5 times 10 to the minus 4th is well below 0.01. So it's a weak acid. Most of it is compound, very little of it is ion, and part of the reason is that conjugate base or counter anion. Fluorine is so electronegative it wants to bind up, so it doesn't want to be an ion. And so what that means with a weak acid, like citric acid, like vinegar, which is acetic acid, like hydrofluoric acid, they're not very strong because you just don't have that many hydrogen ions to do the things that acids do. You know, the different properties that they can do in a chemical reaction. There's just not a lot there. So, and then of course they won't burn your mouth up and dissolve your face if you eat them. All right. Way too many words here, but here's the basic idea then. The common mistake is to confuse pH with strong or weak. Like the lower the pH, the stronger it is, the higher the pH, the weaker the acid is. And that's just not true, right? So my example I put in there is if I tell you the pH is 5, you might think it's a weak acid because it's close to neutral, but that's not necessarily true. It could just be a very dilute, strong acid. Okay. It could be just, again, a very dilute, strong acid that you just, the molarity is very small, so it comes up with a pH of 5. On the other hand, if it is a weak acid, it could be a very heavy duty, it could be a high molarity weak acid. Okay. All right. So, you know, it depends. You just can't tell. It's true. When you're getting to the low pHs, like 1 or closer to 0, even 2 to some extent, it's really impossible to get a weak acid that low. It doesn't dissociate enough to give you the concentration that when you do the negative log of, that you can get a number around 1 or 2. So that's why, yes, with strong acids, the pH is much closer to telling you the truth. Okay. But the reality is you need to know the constant. You need to know what the acid is in the solution, what the concentration was you started with. Okay, so you need to know the acid itself, what's the actual acid, and you need to know its concentration. If you don't know those things, then it's kind of a guess. All right, just off of pH. All right, so that's the idea. So I'm going to show you one type of math, and then really we're going to stop because it's just highlighting what we said about strong or weak. All right. And then tomorrow we're going to talk really about the math that they use with this. And it's a lot of algebra. So we'll get into that tomorrow. And that'll be the big math. This is the easy plug and chug math. So you prepared a 0.1 molar solution of acetic acid. I will tell you right now, acetic acid is a weak acid, but this is going to prove it. At equilibrium, here's your concentrations. The acetic acid compound itself, 0.0987. And each of the ions, the hydrogen ion and the acetate ion, each came out to be 1.34 times 10 to the minus third, which isn't surprising. It's a 1-to-1 relationship. So as it separates out, you're going to have the same amount of ions of each, so the same molarity. It wants you to calculate that equilibrium, that acid dissociation constant. Okay, so here we go. Here's our problem. So our formula would be the ions. So there's the hydrogen ion, there's the acetate ion, there's the acetic acid. You should know how to do this from naming. So that's the formula. Always product over reactant are always the ions over the compound. Plug in the numbers 1.34 and 1.34 times 10 to the minus third divided by 0.0987. When I do that math, it comes out to be 1.82 times 10 to the minus fifth. And then the question is that a strong or weak acid? Well, absolutely a weak acid. It's below 0.01. Okay. Simple plug and chug math, but if you remember how to set up an equilibrium expression from the last unit and do it here, there we go. So tomorrow, ice, ice, baby. What if I only know the initial concentration and I don't know the equilibrium concentration? There's a lot of algebra involved in that one, so we will get to that tomorrow. Until then, just relax and enjoy your day. We'll talk to you later.